All right, so we have started recording. So as I was saying, we'll start with our chapter on torsion. Now, this is a chapter which used to be in the first year mechanics syllabus as per the old curriculum, but in the new curriculum of which you are the first batch, this is part of the second year syllabus, at least in mechanical engineering. Now, will look a little bit new, but ultimately it is just an extension of whatever you studied in your first year. It is more like an application of stresses and strains that you studied in your first year. So without any further ado, let us go to the writing app. Let me share the screen. Can you all see this shared screen?
Yes, sir.
Yes.
All right.
Yes, sir.
Yes, sir.
Okay, let me go to the writing app. Can you see this green colored writing app with this torsion thing written?
Yes, sir.
Yes, sir. It's written.
Yes,
Yes.
sir.
Okay, good. So we'll go into some of the syllabus-wise details in a moment. But before we start, can you just tell me what could be some of the possible applications of torsion? Now, I have not yet defined what torsion is. It is basically some kind of a twisting action on a shaft-like object. Shaft means like you have a stick, a rod, or a beam on which at the ends, if you apply some kind of twisting action, which is very well represented here, as you can see, there is a T dash torque which is applied at one end and a counterbalancing T which is applied at the other end. As a result of which the whole thing deforms in this twisting kind of pattern. Okay, so it deforms in this kind of a torsion. Now, can you give me some real life applications? I had already shared one video with you guys. So a couple of applications is mentioned there. One has to do with the transmission of the power from the engine of a car to the wheels through the transmission shaft. There was another example which was mentioned that in the shaft which is present within the housing of a wind turbine. So the blades rotate and that rotatory motion is transferred in such a way that electrical energy is produced. That is through a shaft also. And because that shaft is subjected to some kind of a twisting action because of the rotatory motion of the wind turbine, you have the application of torsion on that wind turbine shaft also. Can you give me any other example?
Sir, tightening screws using screwdriver.
I could not hear you.
Sir, tightening of screws using a screwdriver.
Right, tightening of screws with a screwdriver. So there is a twisting action involved there, but it is not just a case of pure torsion, because in addition to the twisting motion, you also simultaneously apply an axial force on the screw. So it is a torsion plus axial force there.
Sir, in daily life, we can say about the car, for rotating the wheels, we can use shaft.
Can you say that again? I could not hear.
So in car or in vehicle, for rotating the vehicles.
Right? The steering wheel, you mean?
Yes, sir. In
Yes,
steering wheel.
yes. Yes, the steering wheel, the connection to the entire mechanism, that is a little bit complicated than that. It's not a single shaft, but anyway, yes, there is a twisting motion involved there also. Anything else?
Sir,
So in writing pads which have clip holders.
In writing pads, we have clip holders. Yes. Then.
When we have to put put the papers in position, we have to press it open, so that is causing the deformation where we are like it is kind of like a spring, so at one end it is taller, so when we press it open, we are applying a torsional force at one
Nice.
end.
Okay, I understand what you're saying. Good, good. I like these kinds of examples, real life examples. Well, a card is also a
Sir.
real life example, but this is something which we not directly handle with our on a day-to-day basis, except maybe the steering wheel. Anything else?
Sir, I'm
Yes.
audible,
Sir,
sir.
in torsional springs inside the toys.
So let us not go into torsional springs. Okay, so the case is a slightly bit different there. Uh, let us stick to the examples of stick-like objects or shaft-like objects or beam-like objects at the ends of which you apply some kind of twisting action. At this stage, let us not go into torsional springs. Anything else?
Anti-roll
Yes.
bars in a car. Anti-roll bars in a car.
Anti what bars in a car?
Anti-roll.
You have to be a little bit loud. I am not hearing you clearly.
Anti-roll bars.
What is anti-roll bar?
So it is a bar that connects two wheels of a car to prevent rolling.
Okay, 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 okay. That is far removed
Valve,
from our, yeah, from our day-to-day experience.
tightening of valve.
Tightening of valve. In
Yeah.
which application you were thinking about it?
Industrial valves and boilers and stuff.
You have a twisting action there.
Yeah, that wheel is connected to the shaft, and then you have to tighten it.
Okay. Anything from the human body. So going beyond man-made things to naturally occurring things from in the human body or in the animal bodies
Sir, our neck.
or in from botany also. Yes,
Our neck.
our neck. Right. So basically, if you think about our vertebral column, and if you think of it, if you model it like a, well, it's not a straight beam, it's a curved beam, but still it undergoes quite sophisticated twisting action all throughout its life. That is certainly one example. Anything else?
So just holding your hand and twisting it also comes under torsion.
Yes, when little boys and especially boys, when they fight in school, they generally try to twist each other's hands. So that is also one example of torsion, one very, very close to our real life example of torsion. I mean, there will not be a single boy in school who has not done this, especially in middle school. Okay, so we have some motivation for studying about torsion. Now let us go into some of the details which will help us to understand torsion in a, going beyond the qualitative nature of it, about which we have some kind of an intuitive feeling from our day-to-day life to a more quantitative feeling. And the motivation here is that what are we going to do with this quantitative notions or quantitative understanding? So what instance, what are we going to do about it? So what we are going to do about it is that ultimately you see that suppose you are a designer of a car or a designer of a turbine shaft or in whatever application, the design, it will not be sent by God. You have to design it. And when you have to design it, you will have to understand the highest amount of stresses that are generated in the body and the maximum amount of deformation that the body can or the shaft can sustain without breaking apart. Okay, so how much the maximum deflection or the twisting of the shaft is allowed, and how much the maximum shear stresses or generally the stresses that are developed that can be sustained by the material. So that is the key, or those are the key questions which the design engineer has to keep in mind. And when those questions crop up, the two things which have to be kept in mind are the geometry, certainly, because I mean, it's always a trade-off kind of thing which the engineer has to think about. On the one hand, the lower the amount of material that is used, the lower will be the cost. So it is better and better to have slender members using lesser material. But at the same time, if you make it too thin, perhaps it will not be able to sustain the deformations and the twisting action. So there is always a compromise and a trade-off. And this is where comes into question. So if you have to do, or if you have to arrive at the answers to those kinds of questions, you really have to have a very good understanding of the stresses and strains. So that is the motivation, overall broad ranging motivation. Now, all that is fine, but you have to get into the details. So when it comes to the details, we are interested in the stresses and the strains, definitely. Now, how do we go about finding out the stresses and strains? You see, the input which is available to us, okay, the input which is available to us is that we have a shaft at the ends of which there is some kind of twisting action. So this is the applied load, this twisting action, okay, this torque, this is the applied load. Under the action of this applied load, what you have is some kind of deformations arising in the body. So you see, this kind of a mesh-like thing has been superimposed on the shaft. These are not designs, okay? These are not designs, like some kind of artificial lines have been drawn over this shaft so that it is easier for us to understand the nature of the deformations that is taking place. Okay, so these are some kind of imaginary lines that you see, these horizontal lines that you see, and these circular marks that you see, these are just some kind of imaginary lines, so that this entire shaft is divided into these small kinds of rectangles, and you can understand the deformations of the entire shaft in terms of the deformations of these small rectangles. All right, so this is the undeformed shaft where there is no torsion being applied. And now in the bottom panel, this panel number B, we have this torsion being applied. And as a result of this torsion, you see these little elements which were in the form of rectangles. These are no more rectangles. These have become like rhombus. Okay, so suppose we pick up any one of these rectangles. Okay, and maybe it will be good if I just zoom this a little bit. I hope that is a little bit better. So I'll just delete this thing. So let's say we are considering this rectangle. Now this rectangle has, let's say it's probably this one, something like that. Okay, that has become a rhombus now. So as a result of the torsion, we have this kind of deformation. Till now, we have no idea about the stresses. Okay, but we have to connect, or we have to arrive at the stresses. So what is the motivation here? Who can tell me? What is the connection between this deformation and the stresses? You have to interact with me, okay? Because if I just keep on lecturing, it will be no good. Yeah, tell me.
So in the second, while twisting, the vertical lines are means they are sharing by some angle.
I will come to that part. Okay, there is a certain thing that I will have to highlight, but you just tell me in a very qualitative fashion that we have seen that we are directly seeing this kind of a deformation. There is no doubt that this thing which was like a rectangle, it has become like a rhombus. My question to you is, how do you connect this deformation to the stress? Because this is a question you have to answer in each and every chapter. Yeah, tell me.
The angle at which the lines are rotated.
Right, the angle has changed. So what? So what if the angle has changed? What does that lead to?
Shear strain.
Yes, somebody was saying shear strain. Very good. So whoever was saying shear strain very shyly, it's good. So you see, we have already studied in your first year, and we have also recapped it in our earlier classes, that if we have a rectangle like this, Okay, so please understand that this is a rectangle, very bad drawing, but this is a rectangle, and you can understand that this is one straight line and there is another straight line which is perpendicular to it. So these two are straight lines. Now, let's say this thing deforms. Okay, so in general, we had said that the deformation may take place in this fashion, so that the change in angle from this original right angle, this change in angle, that will be referred to as the shear strain. Now you see this figure here compared to this figure is not quite different from here. The only difference, if you can just so let me erase this thing. The only difference is that what is happening is that these two vertical sides, they are remaining vertical. Okay, the vertical sides are remaining vertical. It is the horizontal sides, these horizontal edges, which are becoming like this. But still there is no problem, because our definition of the shear strain is very general. We had only said that the difference in the angle, that will be giving us the shear strain. So here also we do have a change in the angle from the original 90 degrees, and that will be given by this thing. So when you have this kind of a thing arising, definitely you have shear strain. Now when you have shear strain, what does that lead to? Do you not also have through the Hooke's law or any kind of other material behavior, the generation of stresses? So what I'm saying is that take your mind back to the stress strain relationships which you studied in your first year, the generalized Hooke's law. Okay, and please note that for the purpose of this course, we will always be referring to linear elastic isotropic kind of materials. Okay, as we had discussed in our very first class, we will be interested in isotropic materials, and also we'll be interested in linear elastic isotropic. Okay, we will not be interested in the plastic deformation so much. Okay, maybe here and there we'll refer to it a little bit, but mostly it will be linear elastic isotropic materials. So for those kinds of materials you had studied in your first year, that we have the generalized Hooke's law. So you tell me, okay, what is the connection between the shear strain and the shear stress? I hope you all heard my question.
I guess Poisson's ratio.
I could not hear what you said.
Poisson's ratio, I guess.
Poisson's ratio.
No, so
so
they are
there is-
directly
No,
proportional.
what I'm asking is
Sir,
that
we are ratio
Shear strain and shear stress are directly proportional.
right. So shear stress and shear strain are directly proportional. And what is the constant of proportionality?
Shear
modulus of
shear
modulus.
Shear modulus, right? So we had something like this. So back in our first year, okay, so treat this as the rough column, okay? I'm treating this as the rough column. So we had relations like this. Tau xy is equal to g gamma xy. Was it not? Then we had tau yz is equal to g gamma yz. And then we had tau zx or xz is equal to g gamma zx. These were the three relations. Okay, so in general, you have the shear stress directly proportional to the shear strain. So here also the same kind of thing. Right now you don't have to worry about where is x, y, z. In fact, we will be using a different kind of coordinate system because this is a cylindrical body. In fact, we will be using the r theta z system. We understand that the shear will be something like this. Please note that I am not writing any subscripts here. I will write that a little bit later. Now, coming back to a very important thing which one of you asked. You see, there are some circles present in the undeformed configuration. Okay, so these circles, I mean, if you consider them like discs, they are parallel to these discs. They are parallel to these discs. They are all like, if you line them up together, they're all parallel to each other. Now, in the deformed configuration, question is, are those circles remaining like circles? And even if they are remaining like circles, like the question which I want to ask is that suppose you consider a circle like this from within the body. Question is, after the deformation has taken place, is it possible that points which were lying on this circle, on this flat surface of the circle, they have moved out of this plane? Okay, suppose you consider a point which is here, a point here, a point here, a point here. Is it possible that after the deformation, this kind of a twisting action has taken place, these points move out of the plane? I'm telling you that, and it is quite apparent also from this figure, that these circles are remaining like circles. Okay, but what about the points which are beneath, I mean within it? Is it possible for them to move out?
No, sir, they lie in the same plane.
They will lie in the same plane. Now, you may think, some of you may think that it is quite obvious, but it is not so obvious. Okay, and there is a very, very nice logical argument behind it. I will not go into those kinds of details, and I will encourage you instead to read the relevant part of the textbook. It is there in the 3rd page of the chapter, I think. In our textbook, a very nice logical reasoning is there without writing a single equation. Okay, without writing a single equation, they have explained it very, very nicely. It's a beautiful explanation. Okay, I encourage all of you to take a look, especially the people who consider themselves to be academically serious and are developing some kinds of aspirations towards higher studies. You must make it a point to read that logical discussion. If you have any trouble, ask your questions, ask your doubts in the discussion channel, and I will discuss it separately. But right now, what I only want to say as a fact is that this kind of a deformation where these horizontal lines, they deform, but these circular lines or the circular marks, they do not deform. In fact, the points which are lying within this circle, they also do not deform. This is a very, very special case which you observe only and only for this kind of a circular cross section. This is extremely important to note. Instead of this circular cross section, suppose you had a rectangular cross section like this, a square or a rectangle or even a triangle or an ellipse. Then what I just said, that all these points will remain like this, that is no longer true. So for the twisting action on a shaft having a rectangular cross section, the points in a particular cross section, they may move out or into the plane. Okay, so this plane, it no longer remains like that under the twisting action. Okay, so it can become something like that. Something like that. Okay, where you understand that these things are out of the plane. Okay, but in a circle, they will always remain within the plane. This is a very, very important question which is almost invariably asked in every comprehensive viva. So you understand that now you are in your 2nd year. By the time you are in your 3rd or 4th or maybe 4th year, you will start appearing in various kinds of vivas. I don't know whether in the new curriculum they are going to persist with it, but for all your seniors, they had to appear in their comprehensive viva in their 4th year, 5th year. And these are the kind of questions which are invariably asked. Even if you don't have vivas in the new curriculum, you will have to appear for various kinds of internship interviews and placement interviews. And these are some of the kinds of basic questions which many engineering firms, they ask. Okay, because they don't have to ask you to write any equation or anything. It's just a conceptual thing. Okay, so it'll serve you very well if you understand this thing. Okay, now with all this under our belt, with all this understanding, how can we quantify the stresses? Okay, just arbitrarily writing like this gives us no connection between the shear stress and the driving torque. Okay, the torque which is driving this entire deformation, we have simply no connection between that tau and the t. We want to have that. Similarly, we don't have any understanding of this gamma also. So how do we go about doing that? Well, let's go to the next slide and do this thing properly. So what we'll do is we will consider the deformation of the shaft. So let me try to draw this diagram in as clear a way as possible. it's very nice to draw this diagram on the blackboard, but on the writing app it becomes a little bit difficult. But let me see. So we have this shaft. This is the entire shaft. Okay, this is the outer radius of this thing. This is a solid circular shaft, solid circular cylinder, and we are going to consider a smaller circle within this, concentric with the outer circle. Okay, please do not understand. Please do not think that I'm trying to make a hole in it or anything like that. What I'm trying to draw now is just a circle. Okay, I'm just marking out a circle, but concentric with the outer one. Okay, now I will consider the cylindrical portion associated with this thing. Please understand that this should also be in leave it. I wanted to make that dashed, but I don't want to spoil the diagram. So we have something like this. Okay, please do not think that this is a hole. Okay, there is no hole here. Right. Now you think of this. Suppose I have a point which is present here initially. Okay, in the undeformed configuration, let me consider a point like this. Now, after deformation, after the twisting action has been applied, so let's say that the twisting action is like this. This is my torque T, and I have a counterbalancing torque which is like this, which is T dash, and of course T dash will be equal to T in magnitude. Okay, now under the action of this twisting action, this point, let's say it moves to this point. Okay, as you can see in the previous diagram, the point which was here, it moves up a little bit, as it, giving rise to these kinds of shear strings. So we have this kind of a motion. Now I will draw a line from the center like this, and I will mark out this angle to be, phi. Next, what I will do is I will consider a corresponding point in the undeformed configuration at this other end. Now refer to that horizontal line. I will try to study or observe how much this horizontal line has moved up as this material point has moved up from here to here. Okay, when the twisting action has undertaken, so this point moves to here, and as a result of that, how much this horizontal line it deforms. Maybe it will be better if I draw these as solid lines instead of dashed lines. It will be clearer.
So here the left end is not fixed. We are also applying a torsion of T dash over there. So that point will also be moving.
Yes, yes. So in the most general thing, you do not hold this fixed. Okay, but you can always consider the movement of this thing relative to this thing. So even if this moves, you can consider the actual motion of this point relative to this point as if it were fixed. Okay, it makes no difference. Okay, for the derivation, it makes no difference. So sometimes in textbooks, what is done is that for the purpose of this particular derivation, they actually say that hold this end fixed and move this point, move this end. You can do that for the clarity of understanding, but even if this end is not held fixed, you can understand that there will be a net motion of this point relative to this end. Okay, and in many of the problems, you'll see that you'll have to consider these kinds of relative twisting motions. Okay, so it absolutely makes no, I mean, it's absolutely not problematic. Now, this is a very crucial thing. Okay, so everyone here carefully. So there will be some kind of an angle generated here also. Now that angle, you see, this particular angle that I have just that I have carved out here, you compare with the previous figure. Okay, so this, if I were to draw one horizontal line here, isn't this the same kind of angle?
Yes, sir.
Think about,
Same.
yeah,
Yes,
so
sir.
this is,
It's calm.
yeah,
Yes,
this is
sir.
the same kind of angle. Okay, so this is the crucial mental leap that you will have to understand. So this is the actual shear strain gamma, but be very careful. This gamma that I have just written, this is the gamma corresponding to the smaller circle that I have drawn. Had you considered a circle of slightly larger radius, maybe here, maybe somewhere here, or perhaps even you considered this outer circle on which there would be a corresponding material point here, that material point would have moved out like that, and then there would have been an angle subtended from this point. That angle value would have been different from this gamma value. Okay, so it is what I'm trying to say here is that suppose you considered a corresponding material point here. This material point would have moved up like this here, and you would have some angle subtended at this end. Okay, you'd have some angle subtended at this end like this. That angle, okay, that angle would have been not gamma. Okay, in fact, that would have been the highest value of gamma that is possible. That would have been gamma max. But right now you don't have to worry about all these things. Okay, so let me undo all these cluttering things. Okay, so back to where we started. Now, question is, how do you make this connection between this gamma and the phi and whatever is required? It is through the geometrical considerations. So you see, suppose this entire length, this is capital L. Suppose the entire radius of this thing is capital R. Let me not draw it here. Okay, you understand that the radius of this thing is capital R. Okay, and the radius of this small circle, let's say that is phi. Sorry, not phi, rho. Okay, the radius of this small circle that I have drawn, that is rho. Now you tell me, using this gamma, phi, rho and L, can you give me a relation between gamma and phi?
So L gamma equals to rho phi.
Gamma into L is equal to rho into phi. For people who have understood this immediately, well done. For people who may be taking a minute to understand it, the clue is that you are basically equating this arc. Okay, this arc. Considering this circle, this arc has the length of rho into phi, and considering this particular geometry, that is approximately equal to gamma into L. All right.
Sir, are gamma and phi very small angles here?
Gamma and phi are very small angles. So the entire deformations that we are considering, okay, these entire deformations, I am drawing it in a very big way only for the purpose of clarity, but you understand that the usual kind of materials that we use are metallic materials, okay, or metallic materials, or rather quite stiff materials. So the twisting that is actually induced in these shafts and beams are not in like 25 degrees, 30 degrees, not like that, very small degrees. Okay, and when you do the problems, you will see the actual magnitudes of the degrees through which the twisting action is taking place, and you will get a feel of the actual thing. Okay, so it is very correct that these angles are very small. Now, this means that gamma is equal to basically rho phi divided by L. Very easy. Now you see, go back to the previous slide. Tau is equal to G into gamma. G is material property, which will be available to us because we know what material we are using, and gamma we have just found out, at least in terms of that angle phi. So now we can go back and say that from this information we can say that tau is equal to G into gamma, and this is equal to G into rho phi divided by L. Now one can of course immediately say that what good does this do us, because we still don't know what phi is, and that is absolutely correct. We don't know what phi is, so we have to find a separate relation for this. How do we go about doing that? Well, the key to understanding that is to make a connection with this external torque. Okay, and please listen to this part very carefully, because if you understand this thing, in many of the things, like similar kind of things in the later chapters, you can immediately make a connection yourself. What we'll do is we will take a cross section here. Okay, we'll take a cross section here like this. Not the greatest of diagrams, but okay, we have taken a cross section like this. Now, when you take a cross section like this, what happens is that you are basically kind of considering a cut section which is like this. A cut section which is like this. What I'm saying is that you are making this, you're passing this cut section or cross section, you separate out the thing. Okay, what I'm saying is this, that let me go to the next slide. What I'm saying is this, that after you have made that imaginary cut, you divide the body into the two parts induced by the cut. Now, we had applied this, you see, we had applied this torque. Let this torque be still applied like T. And there was this other torque here, it was T dash. Now you see we have separated out the two bodies. Now as drawn like this diagram is not balanced. These two diagrams are not balanced. So if you consider them like free body diagrams, what is balancing this T dash and what is balancing this T? Because earlier T dash was balancing T, but now these two faces are empty. So what they have been orphaned of any kind of forces. So that cannot be true. This T dash still has to be balanced by something. So what is that something which is balancing this T dash? Equivalently, what is that something which is balancing this T? Quickly tell me.
Reaction.
Internal forces.
Internal forces.
Internal
Very good.
torques and deflection.
Yeah. So internal forces and torques, basically the resisting things which are present on this cross section internally are what are responsible for balancing this T dash and the T. That understanding is the most important thing. Okay, even if you forget all the formula later on, but this basic understanding is what is very important. Now this kind of it, so this is a torque, so correspondingly there must be a torque here. Torque means what? There must be a force, and that force must have some kind of a moment arm. Now logic is very straightforward here. You see this entire cross section, it's a perfectly axisymmetric cross section. I repeat, this is a perfectly axisymmetric cross section. Okay, nice circular kind of symmetry is there. So if there is a T dash like this, definitely you have to balance it out like some through this kind of balancing T. There must be a T here, there must be a T dash here. Okay, and let's just say that I want to represent it by some kind of a T capital I, just to represent this to be generated due to the internal resistances. Now this Ti, can you not imagine that if I consider a little ring, a thin ring here, a thin ring of the cross section, the forces which will be present on this those forces will have a moment arm which will be equal to the radius of this circle. Okay, so what I'm trying to say is this. On this ring, you consider a little element like this. You consider a little element which is like this. Because it is a circular cross section, so I'm drawing an element like this. On this face, you will have an internal force which is like this. So let's say that this element that I have drawn is from this region. Suppose you consider this region. You will have a little element which will again look like this. Sorry. And there will be a force which will be like some small force. This will be some small force. Now you see this force and this force that I've shown, I have given them the same magnitude. The reason is that I'm considering these elements to be lying on the same circle. And over this circle, because of the axisymmetric situation, it really does not matter whether you are considering this region or you are considering this region or this region or this region. No matter which, because they are lying on the same circle, this is the same small circle, and because of the axisymmetric nature of the whole situation, there will be no difference in the magnitude of the forces. Now you consider the center of the circle. Okay, so they are all lying on the same circle, and you consider the center of the circle. Let's say that the radius of this circle, like earlier, it is rho. Now you tell me what is the torque associated with this force. You can call this as dF if you want. Okay, because this is like an elemental force, dF. This radius is also rho. If you consider any other element, it will be same kind of situation. Rho will be the moment arm and force will be dF. So what will be the moment, the entire moment associated from the contribution of all such elements?
Integral of rho df.
Integration of rho df. Now integration of rho df. So let me write that thing. Integration of rho df. Okay. Now integration of rho df, it will be first over the entire this 360 degrees. Okay, from 0 to 360 degrees to cover this entire circle. And then what? We have to go from radius 0 to radius capital R. Remember that the radius of this entire cross section is capital R. So first we have to cover this entire circle, and then we have to go from 0 to R. So this is basically a double integral. Okay, so it is something like this: 0 to twice pi, and then you'll have 0 to R. Okay. Now you tell me what is actually giving rise to this df. We have just written this as df, but how is it? And please remember what we have discussed in the earlier slides. We had talked about the generation of the shear stresses. Anyone?
So the deformation angle or the straight is giving rise to a stress.
Anyone else? How do you connect this df with the shear stresses which was present earlier, which we had discussed in the previous slide?
Sir, by phi.
No, nothing to do with phi or gamma or anything. I'm just asking the relationship between df and the shear stress earlier.
So df of
So df by
d
dA consider
will
the
give
formula.
this.
Right. So it has to be something like this. The df is nothing but the shear stress at a certain point multiplied by the elemental area. I think someone mentioned that, although it was not very clearly audible, but df will be nothing but the shear stress at that point multiplied by the area, multiplied by the elemental area. Okay, so we can very much, very well replace this here. So I'll do exactly that. Okay, let me go to the next slide. Rho tau dA. Now you tell me, what is this dA? Furthermore, you tell me this is a moment that we have drawn, that we have computed. Okay, what will this moment be equal to?
Sir, equal to Ti total T.
Exactly, it will be equal to Ti. It will be equal to Ti, and that has to be equal to T dash, and of course that is equal to T. So the external torque that is applied, that will be balanced by this distribution of shear stresses on a particular cross section. I repeat, the torque which is applied externally will be balanced by the distribution of shear stresses on a particular cross section. Question is, how do you write this dA? So let me write that quickly. You see if it makes sense.
2 pi d rho.
2 pi rho d rho.
Rho d theta into d.
Exactly.
Yes, sir, rho d theta into
So,
dr.
Right. So somebody please tell me in a proper fashion.
So, rho d phi
Rho
d
d
rho.
theta into d rho. Dr.
Rho into
D phi,
D theta.
d
d
theta.
dr
phi
into
rather. Yeah.
And then
To d rho.
D rho.
dr.
into d rho. Very good. Okay, please don't say phi. Okay, because phi we are already using for the deformation. Here we are not writing the deformation. We are only writing the geometrical angle through which we have to traverse. Okay, phi is a different thing. Phi will appear in the expression of this tau. Okay, now you see, because we are in a perfectly axisymmetric situation, there will be no difference in the value of this tau as we go to different angles theta. Whether you are at theta equal to 0 or theta equal to 47 degrees or theta equal to 360 degrees or 298 degrees, it doesn't matter. The value of this tau will be independent of the value of theta, which means that if you actually consider this like a double integral, this tau can very much come out of this integration, which is with respect to the d theta. This tau has no dependence on the theta, so this tau can come out of this. So in the next line, we can write like this: 0 to r tau. Furthermore, you note that this rho is a separate coordinate variable compared to this theta. There is no connection between this rho and theta. They are independent coordinate variables. So we can take this rho square also outside. What will be left with is 0 to 2 pi simply d theta. And therefore, and you have this outside this thing, you have this d rho. You can even put this as a thing.
Hello, sir.
Yes.
Sir, I didn't got why this tau is not depending on theta.
Because it is an axisymmetric situation. Okay, so you consider a circle like this. When you say that something is axisymmetric, it basically means that things which are present on this circle, okay, anywhere on this circle, they have the same value, which is equivalent to mathematically saying that no matter what angle theta you are considering, that entity, whether it is tau or f or whatever, that is independent of this theta. Only then it will have the same value all along this circle. That's what is meant. Okay, so this is simply twice pi. So this is twice pi rho square. What is the expression of tau? Let us take a quick look. Tau is g rho phi by L. Let's write that G rho phi by L. Then D rho 0 to R. Now this is very easy. Take all these things outside. Twice rho is a constant. G is a constant. This phi is a constant, as you can see from this diagram. Okay, so all the material points, they're moving along in such a fashion that such that this phi is maintained. This phi is the entire angle of twist which is seen on a particular cross section. Okay, on a particular cross section, it does not change. It is the same angle phi. So that is a constant with respect to R or rho. So this phi also goes outside. In the denominator, you have L. What is present inside? Tell me.
Rho cube.
Rho cube.
Rho.
Very good. So what we have here is twice pi G phi by L, and then this is R to the power 4 by 4, which basically means that this is twice pi, or not twice pi. This is something like this. You have phi, you also have the G, then this is pi R to the power 4 by 2 divided by L. Now this particular thing, pi R to the power 4 by 2, this has nothing to do with the material property. This is simply a geometrical property of the cross section. Okay, and this is referred to as this is given the letter J, just to write it in short, but this is referred to as the polar moment of inertia. Okay, so this is basically your phi all right, so you see.
Sir, what is the polar moment of inertia?
Sorry?
Sir, what is the significance of this polar moment of inertia?
So the polar moment of inertia represents physically the resistance to the twisting action of a body. And I think this was present actually in your high school physics. High school physics is the mechanics part of +2. If you remember something like the perpendicular axis theorem, if you have something like Ix and Iy, the Ix plus Iy gives you the polar moment of inertia. If you remember that. Okay, you take a relook.
Moment of inertia.
Sorry?
We learned mass moment of inertia, sir.
Right, so mass moment of inertia, you basically have the density of the material present there. This is, you see, okay, since I'm running out of time, what I'll do is I'll one of you just put a question in the discussion channel. It's a very easy thing. I can just discuss it there. Okay, but right now I want to finish up what I'm discussing here. You see on the left hand side, this T is here, and on the right hand side we have this formula phi Gj by L. So overall, what we are going to have is this thing. T is equal to phi Gj by L, which basically means that you now have a formula for the angle of twist. You now have a formula for the angle of twist. Okay, this is something which will be used repeatedly in many of your problems. Phi is equal to TL by Gj. Now, the moment you have this, you can immediately go back to your previous slide where you wrote this expression for tau, which was G rho phi by L, and you can write an expression for that also in terms of the gamma in various things. Okay, so what I'm saying is you have this expression, you have obtained this thing. Since you have just now found out phi, what you can do is you can substitute this thing here. . So tau is equal to G rho phi by L, which is G rho by L, and phi is TL by Gj. So you G and G cancels, L and L cancels, and now you have T rho divided by J. So now what you can see that T is given to us because it is the externally applied torque. J, the polar moment of inertia, is a geometrical parameter which has nothing to do with the material property or anything. As long as you know about the cross section, as long as you know about the radius, you can find it out. So what this formula, this tau is equal to T rho by J, this formula, what it is telling us is the expression for the shear stress as a function of the radius. Remember that tau is independent of theta. So tau will be only dependent on the rho, the radius of the small circles that you are considering. So this formula is giving us the expression of the shear stress as a function of the radius. Okay, so if you consider a circle like this and you sit at any point on it, the tau will have a certain value. If you consider another circle like this, you consider another point, the tau will have another value, increasing, linearly increasing. If you take another thing, this tau will have a certain value here. Now, just looking at this expression, can you tell me what will be the maximum value of the tau? It's an immediate thing, but it is important to realize this.
TR by J.
And rho is R.
TR by J.
Yeah. So the maximum value of the shear stress will be present on the outer periphery of this circle. That's all there is to it actually. So these two formulae, this phi for the angle of twist and this tau, okay, this tau for the distribution of the shear stress, these are what is going to help us to solve many of the problems, and we are going to start solving the problems from Wednesday. I have already gone into the next hour, so please all of you leave quickly and go to your next class.
Sir?
Yes.
Sir, the lines of
all of you can leave. Yeah.
Sir, the line subtending the theta angle, sir, in real life it is not straight, right?
Oh, you mean this one? This earlier diagram that I had drawn? This one?
Yeah, not sir. Sir, that phi angle.
Which one?
Sir, that phi angle.
This
the
phi
circle.
angle?
Yes, sir. Yes, sir.
No, these are straight. These are actually straight. So I had told you to read the textbook, that relevant portion from the 3rd page of the chapter, right? So you will see one nice explanation about this thing also, why it has to be straight. Okay. If you don't understand, you post in the discussion and we can have a discussion about it. Okay. But this is only true for the circular cross section. Okay. For other types of cross section, will not be so straightforward.
Okay.
Yeah.
Thank you, sir.
Thank you, sir.
Yeah, thank you. Please go to your next class.